Welcome to the third part of this module. We will be speaking about graphical representation. Sight is nature's most beautiful gift, and we are aware of this adage, a picture speaks 1,000 words, and we have now seen through our second module that it can also speak 1,000 numbers too. Several tools have been used for data visualization. Text, tables, different types of figures, images, drawings, even diagrams, and finally graphs. Depending on whether we are summarizing data or analyzing data, we can use a combination of all these tools. What are graphs? Graphs are simply a collection of points and lines represented in one dimension. The series of dots and lines represent the values of the variables with reference to a set of axes. The most important point where graphs differ from diagrams is that they are drawn on graph papers, also called as grid papers. Graphs are able to depict the relationship of the variables which are not apparent in the table. They show the distribution of biological variables and therefore allow a comparison with standard distribution like normal, Poisson, and binomial. Graphs require that data should be grouped. The grouping requires that contiguous non-overlapping intervals are established so that each value from the set of observations occurs only once and in only one of the intervals. This is referred to as class intervals. Frequency distributions can be graphically represented as histograms, frequency polygons, frequency curves, and cumulative frequency curves. Let's look at what all we need before making a graph. The most common graph is the Cartesian graph with uniform scales on two perpendicular axes x and y. We need the raw data to be sorted, grouped, and ordered, arranged in ascending order of magnitude, just as we have seen in the part 1 as well as part 2 of this module. The range of data distribution is calculated by the difference between the largest and smallest values. Before we calculate frequency, we need to establish the number of classes, class intervals, define the class limits, and calculate the midpoint as well. How do we establish the number of classes? Sturge's rule is a helpful equation which helps us in calculating the number of classes so that information is not misrepresented in our data analysis. Number of classes depends on number of observations. Usually, an optimum number of 15 is considered. However, range between 6 to 30 is also used. Sturge's rule, simply put as an equation, reads C is equal to 1 plus 3.322 log n, where C is the number of classes and n is the number of observations. Log is the logarithm of the number n. Class intervals are calculated based on the range of the data. This is calculated using the simple formula I is equal to L minus S divided by C, where L is the largest value and S the smallest value. Class limits define the boundaries of the class, that is the lowest and the highest values which can be included in a given class. Lower limits are represented as L1 and upper limit as L2. These values help in calculating or establishing the mid value or the midpoint. The sum of the two L1 and L2 is divided by 2 to arrive at the value of the midpoint m. For example, the class 10 to 20 has a lower value or limit of 10 and an upper limit of 20. The midpoint is 10 plus 20 divided by 2, that is 15. Based on the class intervals, data can be classified as exclusive or inclusive. For continuous variables, exclusive method is used where the upper limit of a class is the lower limit of the succeeding class and thus there is continuity in the data. For example, classes 10 to 20, 20 to 30, 30 to 40. Here, no data point is missing and no extra class boundaries need to be defined. For a discrete variable, the inclusive method is used where the upper limit is included in the same class. For example, 10 to 19, 20 to 29, 30 to 39. In this case, we need to define additional boundaries, which are defined by subtracting 0.5 from lower class limit of every class and adding 0.5 to the upper limit of every class. These will be more clear as we deal with an example. Let's look at how we finally plot and work on that paper which we call as the graph paper. Construction of the frequency graphs on the graph sheet requires us to divide the entire sheet into 4 quadrants numbered with the Roman numbers as 1, 2, 3 and 4. The horizontal and vertical lines that separate the quadrants form the x and the y axes. Horizontal lines are referred to as the abscissa and the vertical as the ordinate. The point where they intersect is called the point of origin, O. Abscissa and ordinate together form coordinates of the point. This is what you send when you say, please send your location. Let's see how the points A, B, C and D can be plotted on a graph. These are represented in the 4 different quadrants with the following abscissa ordinate values. In the first quadrant, point A is represented with the abscissa value of +2, ordinate +2, and therefore the coordinate can be written as +2, -2. The same way, the description of each and every point in the different quadrants is given. Let's look at how it appears on the graph. The red dot represents point A. It has been plotted using the value 2 on the x-axis and 2 on the y-axis. Similarly, for point B, the blue dot has been placed where the points -1 on the x and the 2 on the y-axis meet. Similarly, point C has been plotted as a yellow and the D as the green dot. The point of origin is also marked on this plot. While constructing the graph, how do we decide what variable to place where? Usually, the independent variables are plotted on the x-axis or the horizontal axis. The independent variable is the one that we are manipulating or varying in the experiment. The dependent variable is plotted on the y-axis, which is the variable which is the one we will be observing during the experiment. However, neither of the variable is sometimes manipulated, whereas both could also be only observed. In such cases, we can test the hypothesis that changes in one variable would cause changes in the other and therefore decide to put the variable which is causing the change on the x-axis. There may be times, of course, where there is no cause and effect relationship and we cannot plot either variable on the x-axis. There are situations where it is common to put the independent variable on the y-axis as well. Such an example is one where oceanographers measure the distance below the surface of the ocean on the y-axis. The top of the ocean is represented at the top of the graph. The independent variables like salinity, fish abundance, chlorophyll concentration, etc. is represented on the x-axis. The most common type of graph is the histogram. This is a very simple graph which is prepared by drawing a set of vertical bars whose area is proportional to the frequencies represented in our data. As opposed to a one-dimensional bar graph where only the length or the height is important, the histogram is a two-dimensional graph where the width as well as the height both are important. Each bar is essentially a rectangle with the width that represents the class interval and the heights that represent the frequency. The number of classes, class intervals, class limit, and midpoints are calculated just as we described earlier. Class intervals can be equal or unequal when we are plotting the histogram. If class intervals are unequal, a small correction is made to adjust the frequencies by calculating a variable referred to as frequency density. Frequency density is calculated by dividing the frequency by group width, where the group width is the adjustment for the unequal class interval. Let us look at an example to clarify the concepts on histograms. Here we have a data set with beak depths of 25 finches. These are small birds where beak size has helped in adaptation. This data shows us that the values are continuous, ranging from a minimum of 7.5 mm to a maximum of 11.2 mm. I hope that as you watch the video, you will also do it yourself. So let's prepare a frequency table.
The data has been sorted in an ascending values with values from 7.5 to 11.2.
Below that is a frequency table where we have added two new values, 7 mm and 12 mm. Both these values are limiting our entire data set. On the right hand side, we see a table that lists the descriptive statistics value as you have learned in other modules, and you are well aware that these values can be easily depicted on a simple bar chart.
Based on the Sturge's rule, the class interval for this data works out to be 0.655 or approximately 0.7. But for ease, we have created the classes with class intervals of 1. You are aware that we can easily create a bar chart reflecting this data. It is also helpful to note that variety of enhancements are possible to this bar diagram. For example, mean, median, mode, standard error, standard deviation can also be marked. So why do we need a histogram? Let's plot a histogram. This graph has been plotted using Google Sheets. Here we can clearly see that both the class interval as well as the frequency are reflected in the height as well as in the width of the rectangles for each class. The frequency, that is the number of birds which fall into each category of a beak depth, are clearly visible. This histogram tells us about the overall spread of the data and also indicates the variation is continuous within the range of 7 to 12 mm.
The frequency polygon is a type of graph which is constructed by plotting variables on the x and y axis just as we do for the histogram. But the difference is that the polygon uses the midpoints as the key feature. The polygon is just a simple line graph which connects the midpoints of all the bars in a histogram. Let's see what it looks like. The midpoints of each class is represented by a dot, and the height at which the dot is placed is the frequency of the relevant or the respective class intervals. The dots are connected by a straight line to get the frequency polygon. This is how a frequency polygon would look for the histogram of the beak depth that we just worked on. The dots are showing the midpoints, and the line that joins are straight lines which are connecting all the dots. The next is the frequency curve. Histograms and frequency polygons approach a form of a smooth curve. Such a curve is obtained in a normal distribution of individuals in a large sample or in a population. This sample frequency curve actually serves as a measure for the population frequency and is used very frequently in statistical analysis. For a majority of biological characters, distribution of frequency approaches what is known as a normal curve, which is bell-shaped. The area under this curve is equal to the area in the frequency polygon or even the histogram.
Let us look at an example to check our concepts on preparing frequency curves. Here we have data on the length of spike in wheat plants. The data consists of discrete values, and we can start by sorting and arranging it in ascending order. We will use Sturge's rule to calculate the class intervals, which works out to be 3. The frequency table can now be prepared using tally method as well. Let us tabulate the class intervals and frequencies as well as list the midpoints. As you can see that with spike length values ranging between 17 to 19 centimeters, the midpoint is 18 and the number of plants or the frequency is 2. Similarly, we go down using all the 25 values in our data set and plot a curve. This hand-drawn histogram shows you something very close to what we have seen in our earlier example as well. Plot on this histogram the midpoints of each of the interval classes. Now connect the midpoints using a smooth line passing through all the midpoints. You will arrive at a similar graph to the one that's hand-drawn and plotted here for you. This can also be drawn using softwares. So for example, here is the same frequency curve plotted using Google Sheets. Note here that the curves are reflecting the distribution of the data and indicates a very specific statistic that is used to describe data. Softwares like Excel, Google Sheets, and many others allow for the creation of a variety of simple graphs.
The cumulative frequency curve or the ogive is another type of graph, and this is a very unique type of graph. This is made when we wish to consider whether the number of observations are falling above or below a certain value rather than falling within a given interval class. For plotting such a graph, we need the conversion of our data or a calculation of the cumulative frequency. There are two methods by which an ogive can be made. The less than method, where we are plotting a rising curve and we start with the upper limit of the classes and we add the subsequent frequencies. The second method is also known as the more method, and we plot a declining curve by starting with the lower limit of classes and adding subsequent frequencies. Let's see the example which is here before us on the number of grains per spike and the number of plants that are showing the number of grains. We will prepare a table for the lower and upper class boundaries and then calculate the cumulative frequency values. Class boundaries are calculated by subtracting or adding the difference between the upper limit of one class and the lower limit of the preceding class. So here we will be calculating and establishing the lower boundary as 16.5 and the upper class boundary as 19.5. Let's see how this table will look like. I will go over a few values. For the first row, the number of grains per spike is between 17 and 19. The class interval therefore has the lower value of 17 and an upper value of 19. The midpoint would be 18. The frequency, that is the number of plants which are showing these number of grains per spike, is 8. The class boundary would be 16.5, 19.5. This is based on what we have earlier read on how to calculate the class boundaries. We calculate the relative frequency by the formula f divided by n multiplied by 100, with which we arrive at a value of 6.15. The cumulative frequency is then calculated using the formula listed. Here we can see that when we make a table for the less than and the less than graph, which will be where we use the upper limit of the classes, the number of plants in the upper limit 16.5 is 0 and a cumulative frequency is also 0. 19.5 gives us 8 plants and the cumulative frequency is 0 plus 8, which is 8. As we go down, the number of grains for the upper limit of 22.5 gives us the value of 8 plus 15, which is equal to 23. As we go down, we will be able to reach the final number or represent the cumulative frequency for the less than graph. Similar way, we calculate the number of grains for the more than graph using the lower limit of the class. So here we see that number of grains are more than 16.5. What would be the number of plants? It would be the sum total of all the plants because 16.5 is the lowest value in our data set. In such a way, we can actually make out the difference between the two cumulative frequency tables. One starts from 0 and ends at 130 in the cumulative frequency column, and in the second one, where the more than values are listed, we start with the 130 plants and we end up with 0 in the cumulative cumulative frequency column. This data is then used to plot the curve for the declining and the rising curve, where the cumulative frequency or the ogive is made. As the number of grains per spike increases, we can see the change in the number of plants. There are several advantages of graphical representation of frequency. All these four methods have given us a very simple way in which we were able to compare which of the observations was most frequent in our data. It also showed us a trend and not just the value of the statistic. All the four have also revealed relationships which we were not really able to see in the comprehending tables as well. But there are several limitations to these. The graphical representation of frequencies are not completely accurate and not all values are getting represented. Few characteristics get depicted on graphs. However, we have to also guard against providing any misleading information, as just trends and fluctuations and tendencies can be visualized. To sum up our analysis, as well as the way that we have looked at visual representation of data, we can see that the type of data and the nature of analysis dictate what type of graph or a plot or a diagram we wish to use. For discrete data, The descriptive information comes from bar charts, pie charts, pictograms, and stem plots. A comparative analysis for discrete data can be seen by pair of bar charts, a pair of pie charts, compound bar charts, component bar charts, back-to-back stem plots. Continuously varying data can be analyzed, can be described using histograms and stem plots. The comparative analysis of continuous data also requires a pair of histograms, back-to-back stem plots as well. Paired data usually is studied for correlative analysis, and this requires the preparation of scatter graph, time graph, which are a more advanced way of representing data. Visual representation softwares and platforms have seen a large profusion in the coming times, where data analysis has become the key word, or a very much common term. A large number of softwares have been developed which fulfill the requirements of exhaustive types of experimentation and questions that have been asked and are being asked in biology. The effort that we have made here has been to simply build a basic perspective on how to summarize data and build graphs and diagrams. Many other basic types of graphs and graph papers are used besides the simple graph that we discussed. For example, logarithmic graphs, semi-logarithmic graphs, square law graphs, polar graphs, which are commonly used for biological data analysis. Simple plots like the stem plot, box and whisker plots are also used in biological data representation. As new technologies and methods develop, new types of representations like heat maps, etc. have been evolved. Some of the common data analysis packages like MS Excel and Google Sheets, SPSS, the Sigma plot, ggplot in the R package provide ample visualization tools. This fundamental module, which will help you to navigate how the simple clicks on a tab in the software lead to the graph. We have used and considered a lot of examples and content that has been published on these several websites and very key books. We thank you for your patient watching of the video, and we look forward to connecting with you for any discrepancies, suggestions, and any details that you would like for the examples discussed. Thank you.